All right. So what I taught you back then on how to do metric conversions, you're going to be happy because you're going to be confused. I'll be very shocked if you're not confused. Somewhere in the first 15 minutes here, what I'm about to do is the first really difficult concept probably in chemistry you're going to see. All right? And you're going to find by the time I'm done, what you're going to shock you is how easy it is because of how I taught you this system before. You won't have to understand both the conversion factor system and Avogadro's number, atomic mass, and moles all at the same time. Those three numbers didn't mean anything to you. Okay. First of all, let me talk a little bit about atomic mass. The atomic mass is not what you're thinking. As a matter of fact, let me get out of this for a second and show you something. Oh yeah, I got to escape out of here. Look at the periodic table here. Okay. If we look at the periodic table, I hope no one, when doing those worksheets, was using these numbers and rounding them up. First of all, I just told you that right at the beginning of the period not to do that. All right. And secondly, I'm going to explain what those numbers actually are. Those are the atomic masses, not the mass numbers. It should be obvious they're not the mass numbers. The mass numbers are protons plus neutrons. How do you kind of know that none of these numbers could be the mass number? What about them tells you that as you look at them? They're decimals. So it's going to be a whole number. It's always going to be a whole number if I can have mass number something plus 5 plus 7. It's always going to be a whole number. So that's not what these are. They're often close, and you're going to find out why they're close in a little bit. All right. So I'm going to tell you about this number first, what it means. All right. And then I'm going to show you how he's related to two other numbers, two other things, two other terms. All right, that will make your life miserable and a lot easier. Okay. I don't quite understand how that can be, but you'll see in a second. All right, let's start with the miserable part. Let's start with the part where I have to explain some stuff to you that you're going to be, within 10 or 15 minutes, a little confused. Atomic conversions. And we'll start with atomic mass. All right, atomic mass. It's not the mass number. See, the problem with the real masses of these atoms is that they're so ugly. They're so small. What do you think the real mass of a carbon atom, for example, is? Yeah, it's going to be like something like 0.0. Oh, I don't want green. Like 0.0. Still green. Wow. Seriously, I've hit this 15 times. Finally. Okay. 0.000000000 20-some zeros. Okay? I don't want to write that number down. So, yeah, well, we don't have to. I already taught you how to do the, whatever, 4.8 times 10 to the negative 20. I still don't want to write that number down. It's an ugly number. Chemists, scientists, maybe nerds, but they're not stupid. No one wants to write that kind of a number down. Whether it's in standard notation or scientific notation, it's an ugly number to deal with. So you know what they said? Let's make our own system. We'll make our own weighting system. And we'll make everybody on the periodic table weigh nice normal numbers. That's why those numbers on the periodic table I just showed you were normal size. 12.011 for carbon. 30.974 for phosphorus. Okay? They were normal numbers. I could write them down. They're not hard to deal with. So that's what they did. They come up with their own system, so we don't have to write these ugly numbers down. Let me show you kind of how they did that, all right, in a second. But first, just copy that down, the definition of mass, atomic mass. It's the mass of an atom expressed relative to a single atom, and that atom that they chose was carbon-12. All right? It's expressed relative to him. It's a relative scale. It's not an absolute scale based on a standard weight of measurement. Well, I guess, in fact, carbon-12 is our standard. But let me show you kind of what they did. I'll make a little chart here for you, okay? Do not copy this chart. There's no reason to. Just watch. I'm going to take people's masses. You're all periodic table elements. Everybody in this class is an element of the periodic table. Just like that, you all weigh different amounts. So I'll take your actual mass and your new mass, your relative mass, on my new scale. Okay? Let's take someone of about average, in between, in the middle probably. We'll take Zach. Now, I don't know how much Zach actually weighs, so don't worry, I'm not going to call any girls. I learned my lesson a long time ago. Zach, you weigh probably around 150? Close enough. That's what you're going to be. So Zach is our standard. We choose Zach because he's going to be somewhere in the middle. All right, 150 pounds is his regular weight. On this new scale, now that's, by the way, that's not an ugly number. That's not like 0.0000000. Yeah, it's not some ugly number. But they are. Those on the periodic table are ugly. So we decided to make it just 12. The reason they chose 12, I'll tell you at the end of all this in a minute. Okay, Zach is now 12 atomic mass units. These new units. That's your new weight. Okay, lost a little bit of weight. Now, let's say I take somebody who's very tiny, very small. We'll take, again, only choosing males. Jared probably weighs about 100 pounds. Probably a little bit more than that, but we're going to say 100 for nice, easy numbers, right? So we'll take Jared. Say about 100 pounds he weighs. Okay? Now, can anyone tell me what Jared's weight would be on our new scale? It would be 8. It would be 8 atomic mass units. Now, some of you are probably saying to yourself, well, how the heck did he get that? Well, there's two ways. He may be looking at it in a proportionate way of how much Zach weighs more than Jared, and that works. Or you could use the system I taught you in the metric conversions. Remember? I could take Jared's actual weight. Well, you're not copying any of this anyway. Jared's actual weight is 100 pounds, right? And I could do a conversion. I could put pounds on the bottom and these new atomic mass units on the top, and I just said Zach was our standard. So Zach is 12 in this scale and 150 in this. Guess what happens if you multiply all that out? Guess what you get? You get 8. Exactly. Now, even if you didn't understand where Ben got that from, I bet everybody now can do my maths because I weigh around 200 pounds, about 195. All right, so this is me. I weigh about 200. What is my weight on the new scale? Everybody knows it's going to be 16 because I'm about twice as heavy as Jared in real life. And I'm twice as heavy as him in my new scale. It's exactly what they did for all the elements of the periodic table. And you realize I could take any of your weights, whatever they are. They could be 125, they could be 130, they could be 300, it could be any weight at all. And I can convert them using Zach as my standard. He's my standard. I put a big box around him, and I can just use him as my standard to convert everybody. That's what they did with carbon. You might wonder, why did they choose carbon? All right, well, there's a couple of reasons why they chose carbon and why they chose it to be 12 and not just make him 1 or something like that. They chose 12 for a very good reason. Carbon 12 would have how many protons? No, he would not have 12 protons. I hope he didn't do that on the worksheet. How many protons would he have? 6. How many electrons? I'm sorry, it doesn't matter about electrons. How many neutrons would he have? 6. That was what makes him carbon 12, right? So if I chose 12 as my atomic mass, wouldn't it be right with the atomic or the mass number as well, right? The mass number is 12 and the atomic mass is 12. Now some of you are probably thinking in your head, but up there it says a different number. It doesn't say exactly 12. I'll get to that, why it does that. It has to do with the isotopes. We'll learn about that probably tomorrow or Monday, okay? All right, so, but the reason they chose carbon 12 and made him exactly 12 is so that the mass numbers will be very close to the actual relative atomic masses. That's why they did that, all right? And they chose everybody. If you know everybody else around there, if you were doing your homework, you were noticing in that worksheet, most of those numbers up there are similar to the mass numbers. They're not exactly the same, but they're similar to them. All right, good enough. So everybody, I think everybody pretty much understands this first concept, why they did it. They did this so that we would have a scale that makes more sense than writing down the actual mass of an atom. Problem with that. We now have a number that is a nice, easy number to write down, but it's not useful. It doesn't really, I can't hold a carbon atom in my hand and do an experiment with it. We generally do experiment with larger amounts. So although it's a nice number to write down, it's not a very useful number. So they said, you know what would be really useful? If that 12, oops, wrong one. All right. if that 12, instead of being in these atomic mass units, boy, wouldn't it be nice if that were in grams? And they said, well, let's do that. We'll call it the gram atomic mass. The atomic mass in grams, 12 grams of carbon. And they realized 12 grams of carbon is going to have a lot of atoms in it. How many? It's going to have 6, 0, 2, 2, 0, 0, 22 zeros, 6.022 times 10 to the 23rd. That's how many atoms would be in 12 grams of carbon. Guess what? That's how many atoms are in the atomic mass of any element in the periodic table. It's called Avogadro's number. And it equals 6.022 times 10 to the 23rd. That's Avogadro's number. Now, I'm already starting to lose people, and I can tell. And it's going to only get worse as we go on, because I've got to bring this all back around in a few minutes. But try to stick with me here. Avogadro's number is 6.022 times 10 to the 23rd. That number is the number of atoms in the atomic mass in grams of an element. It's the number of atoms contained in the gram atomic mass of any element, or of any atom. Okay? So if you look at your periodic table, which I want to do here, grab this periodic table. If you look at this periodic table, here's what I'm saying. This is, by the way, the periodic table up there you can probably see a little bit better. I'm saying boron weighs 10.811 grams. Boron atom weighs 10.811 atomic mass units. 10.811 grams of boron has 6.022 times 10 to the 23rd atoms. 24 grams of magnesium has 6.022 times 10 to the 23rd atoms. 126 grams of iodine has that. How can different masses have the same number of atoms? How can different masses have the same number of atoms? Because each atom weighs a different amount. Think about it. Think about this. Say you've gone bowling, right? I'm sure. Say I work at the bowling alley, and I got a shipment of bowling balls. Bowling balls go by weight, right? So let's just make up nice, easy numbers. Say you had 10-pound bowling balls, and you got a shipment of 10 balls. How much did that box weigh? 100 pounds, right? You see it? Make sense? Now let's say I had a shipment of also 10 bowling balls, but they were 15-pound balls. You pick up that box, how much does it weigh? 150 pounds, right? So you can have this different weights, different masses, for the same number of balls, because each ball weighs a different amount. And you can have different masses for the atomic masses on the periodic table. Let me go back to that for a second. These all have different masses, but contain the same number of particles. Avogadro's number of particles. I'm losing people right now. It's okay. It's all right. Don't worry. We're getting back to it. All right. Back to this one. Got to get back to where we were. Well, we've covered atomic mass and Avogadro's number. We've recreated a problem. Here's the problem we've recreated. Our original problem was the mass of carbon, or any atom, is really ugly, small. Really a bad number. I don't want to write it down. So we made up the atomic mass scale and gave it a nice, easy number. Nice, easy mass. Problem with that was it's not very useful. Can't really work with one atom at a time. So we said, let's have it in grams. Great. Only problem is that contains a very large number again. You're back to where you started. You got an ugly number you want to get rid of. So we do one more thing. We call that number something else. We call it a mole. A mole. This will take care of both problems. Okay? If we call this guy a mole, kind of like, you say, well, first of all, what do you mean by call it a mole? Here's what I mean by that. When you buy your eggs, what do you buy them in? A carton of what? How many? A dozen. Your parents probably don't say, go to the store and get me 12 eggs. They say, go get a dozen eggs. When you buy pencils, they come in 144. What do we call that? A gross. When you weigh something that's very heavy, like a car, you don't weigh it in ounces. You weigh it in what? Tons. See, for large numbers, we generally have a term that means the same thing. Just like 12 means 1 dozen. Just like 1 gross means 144. Just like a ton is 2,000 pounds, 1 mole is 6.022 times 10 to the 23rd. It is basically that guy. All right, maybe not, but he is a mole. He is the amount of substance containing Avogadro's number of particles. I can have a mole of pencils, just like I could have a dozen pencils, just like I could have a gross of pencils. I can have a mole of pencils. It would be a lot of pencils, but I could have it. But towards the end here, I'm trying to show you how we've come full circle. I'm going to make this point one last time, and I'm going to leave it alone. Now, I told you these first 15 minutes were going to be rough, okay, to explain. And I'm sure I've lost a few people along the way. I'll try to sum it up one more time. The beauty of this is, even if you are a little confused at the end of this, you won't be confused when I flip this board and we start doing problems with it. It will be very easy. The reason it'll be very easy is because you already know how to do conversions. All right, take a look. Sum it up one more time. Real mass of an atom, ugly number. We make up our own scale. And there it is in the periodic table. It's right there. Those numbers down there, 12.30.9. Those are the mass in the atomic mass units. Lousy number. Can't use it for anything. So we put it in grams. That number in grams contains this many particles, and we call him a mole. Why are moles nice? Because they solve both problems. A 1 mole of carbon, just a simple number, 1 mole of carbon, okay, it's that many grams, and I can work with it. I can work with that. And it's also not an ugly number to write down, okay? But it kind of mirrors and mimics atoms. All right, so if you don't understand that, which I'm sure you don't, 100%, it's okay. But I am going to go on and show you how to do problems with this, where I will convert atomic mass grams to the Avogadro's number to moles. Yeah.
Why? Okay, I understand, but why 6.022?
Well, again, it's not that there's why, where we just like if you take the atomic mass, all right, of any of these guys, that's how many are in there. That's how many are in 1 mole. Okay, the atomic mass of. So basically, if you pick a guy out there, nickel. See nickel over there, 58.69. 58.69 grams of nickel contains 6.02 times 10 to the 23rd.
So they just came up with that.
They didn't come up with it. That's how many are there.
Because of what was on there.
Because of the original scale you made. They arbitrarily picked 12. Okay? Arbitrarily picked 12. It wasn't arbitrary. You wanted to have 12, so it would be close to. If they had chosen as their standard instead of carbon, if they had chosen somebody else, or if they had said, you know what, instead of carbon being 12, let's make him 1, or let's make him 100, then that number would not have been 6.022 times 10 to the 23rd. It would have been some other number. All right? But that's the only reason why. But again, if you're confused on this 100%, it's okay, because this is all you need to know. What's in that boing, 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 boing box right there is all you need to know. And I want you to put a big box around that. And that's going to be on my board. Marvin, put a big box around that. And that's going to be on the board right up here for the rest of this chapter until the test. That big box is going to be up there for the rest of this chapter. And that's all you need to know. Of all that I've said, I mean, it would be nice if you understood it. It would be nice. But I'll be totally honest with you. You don't have to understand it. You totally don't have to. As long as you can understand as long as you can remember what's in that box, you can do these kind of problems. Copy that. Don't. You already have the box copy. Just copy that example now. That's a bit of a cop-out, a bit of a cheat, saying you don't have to understand it. But I realize that most of you don't care, first of all. And that's okay. Like I said, I'm not here to teach you like you're all going to be chemists someday. I did my best to explain it, and if you want it, you can look it up yourself and I can tell you more about it. But here's all that matters. Do you remember how we did conversions in the metric system? If this question had one thing different, just one question, one thing different, if instead of saying how many moles, it said how many kilograms, one word different, or in 24.7 grams of sodium, what would you have done first? What would you have written down first, Ellie, if you wanted to do a conversion? Good. 24.7 grams. So let's do that. 24.7 grams. If we were doing a metric conversion, what units would you put on the bottom, Maddie? Everybody agree? You put a gram at the bottom? You put grams at the bottom, not because grams always go on the bottom. How did you know grams go on the bottom, Josh?
Which one?
You.
So they cancel out.
The Joshes do cancel out, and so do the grams. Right. Okay. Now, what goes on the top? Well, if it was asking you for kilograms, you put kilograms at the top. This guy's asking you for something else. It's asking you for moles. So, what goes on the top? No, moles. That exact thing it asked me for, moles. Don't read anything into it. What I just did there is, remember when we did dorks and dweebs? Remember that one? Same thing. You didn't even, does it matter what a dork is? Besides me? No. We were able to do that conversion on that worksheet because I gave you the conversion factor. And guess where the conversion factor is? Here. Right there. You're not going to believe this. You're not going to believe this, but these conversions, what I'm doing right now, will actually be easier than the metric conversions. Easier than going from meters to centimeters and centimeters to hectometers. Easier than that. You say, I don't believe you. I can show you your test when you're done. I'll bet you more points were lost on the first test in the 4 problems than you'd have lost on this test on the problems I'm going to give you like this. And here's a good reason for that. A lot of you mixed up deca and deci, or hecto, and didn't memorize them. There were 6 things to memorize there, right? Kilo, hecta, deca, deci, centi, milli, right? How many things do you have to memorize here? 1. Well, basically 3, but really only 1. That number right there. It's the only number you have to memorize. Because when it comes to the atomic mass, how will we know what goes next to grams in here? Do we have to memorize that? No. It's the atomic mass. And where do you get the atomic mass from? The periodic table. Look on your periodic table. I'll skip ahead here to show you the periodic table again. What is the atomic mass of sodium? It is sodium I'm doing this one, right? Look over here on sodium. There's the atomic mass, 22.990. Everybody see that? It's on your periodic table and on the one on the board. Okay? And let's go back to it. So I put 22.990 grams. What goes next to moles? Look in the box. What's next to moles in the box? No. What's next to moles in the box? 1. 1. That's all you have to do. What's in this box tells you everything you need to know. And there are only 3 things in that box, not hecta, deca, deci, all that stuff. And only one of them needs to be memorized. This one. I mean, do you really have to memorize 1? You don't have to memorize this. They're on the periodic table. So, go get your calculator out, do the division for that. What do you get for that answer? It's like a cricket. A cricket when it's cold outside. When it's warmer. You know you can tell how warm it is by how fast the cricket chirps. Did you know that? Mm-hmm, mm-hmm. Okay, what do you get?
1.07.
1.07, you say? Is that right?
Yeah.
Yeah, no, yeah, no. What do you have?
Oh, I was going to add the other decimal place.
Oh, no. We have 3 significant figures. I mean, I don't know if that's the right answer, but assuming it is the right answer, that's the right number of significant figures. Anybody get some other number different than 1.07? No? Okay, good. Remember, the answers are the least important part. If you've shown all this work, how many points are you going to lose if you accidentally hit the wrong number in the calculator? 1. Okay? All right, next. Try this guy.
Wait, is this supposed to be grams?
Oh, yeah, I'm sorry. Didn't I put him? My fault. Grams next.
Grams.
Yeah, grams next to it. Yep.
Moles.
Huh? Oh, right. I'm listening to Emily, which was my first mistake. Yes, it's a mole. Sorry. And again, why is it moles? I wasn't paying attention. Because grams canceled and leaves me with moles. Okay? All right, let's go to the next example. How many atoms are in 2.1 moles of carbon? Can you do this one? Sure. What are we going to write down first here? What do you think I should write down first? Trent?
2.1 moles.
Correct. 2.1 moles. Bo, what unit's going to go on the bottom? How'd you know that? You have to cancel. What units are going to go on the top? Just the units. I don't want a number. What units are going to go on the top here? Ronnie? Just read. Don't.
Okay. Atoms.
Atoms. And Eves. Okay. What goes next to moles? Every single time you see moles, what goes next to it? 1. Now hold on. I want to stop here before I get to the next one. Some people heard, and will swear on a stack of Bibles, well, you said moles always go on the bottom. Every single time moles go. Did I say moles go on the bottom? What did I say? I said you'll have a 1 next to moles every time. I didn't say it goes on the bottom. Notice it's on the top up here. It's on the bottom down here. I never said something always goes on the bottom. Or you follow the units like you always did, even with the metric conversions. Okay. What goes next to atoms? This number, 6.022 times 10 to the 23rd. Now, you may realize now why I was teaching you just a few minutes ago how to use your calculators to plug this in, right? Do that again. On your calculator, what are you going to hit? 2.1 times 6.022. And I'm going to know if you did it right or not because we'll see if you're off by a decimal. If you've forgotten something I just told you, you'll be off by a decimal point. Hopefully you plugged it in the right way using that exponent button, the EE button, EEXP or EE. Who's got an answer for this one? What do you got, Josh? The other Josh. 1.2 times 10 to the 24th. Did everybody get that? Anybody get a different exponent? Here's probably what you did. When you plugged this in your calculator, you plugged in 2.1 times 6.022 times 10. No. It's 6.022 exponent button. Because you know what the exponent button means? It means times 10 to that power. So try it again. 2.1 times 6.022 exponent button, not times 10 exponent button. 23. And then you'll get the right answer. Hopefully. All right? Most of you did get it right the first time, though. Looks like. All right, good. All right, last one. Last example. You ready? What's the matter? Oh, yeah. Again, what did I forget again? Moles canceled. Leave you with atoms. Good thing. And by the way, on the test, I mean, granted, when I'm teaching, I tend to forget little things like this. On a test, you guys have to remember too. But the good news is I know we're all making dumb mistakes. I make them all the time too. How many points will significant figures and units cost you on a test? Half of a point. 1/2 of a point. Not even a whole point like the wrong answer does if you plug it into the calculator wrong. 1/2 of 1 point. So if you forgot your units here like I did, or if you put the wrong number of significant figures like somebody wanted to do up here, that's a 1/2 a point per problem. Okay. All right, last one. Oh, right there. All right, so copy that guy down. We'll see if you all set it up right. Hopefully you all wrote down the given information first. You all multiply by atoms on the bottom. I just realized something on this one. I bet some people were confused. It doesn't specifically say what units to put in the top, but it implies what units have to go there. Kind of the same way I'm implying when I say I'm 6'2", what am I talking about? My height. And if I told you I'm going to tell you my weight, what units am I going to use if I'm going to tell you my weight right now? Pounds. If I want the mass, what units do they have to be in? Exactly. Now, next to grams, we'll go. Remember your box that had the 3 things in it, right? What goes next to grams every time? The atomic mass, right? The atomic mass goes next to grams every time. There's grams, there's atomic mass. What's the atomic mass of boron? 10.811. You get that from the periodic table. Okay? You don't pull that out of your hat. That comes from the periodic table, which we just saw here. There's boron, there's 10.811. What do I put next to atoms? Every time this will go next to atoms. What is it going to be? 6.022 times 10 to the 23rd. Every time. Now, some of you also, I told you the math was a little bit harder in this one. Some of you also may have been thinking to yourself, well, I don't know how to multiply or divide that out. Sure you do. Can you do this? 2 times 1 over 2, or 4 times 2 over 8. Can you do those? Because you probably could have done those in 4th or 5th grade. If you can do this, you can do this, you can do this, because you have a calculator. Okay, a calculator will do it for you. You'll take this number plugged in correctly times by that number, and then what will you do? Divide it by the denominator. Got it? Let's see what you guys got for an answer. What did you guys get for an answer in this one? 43 point something else? Yeah, where am I going to round? And I got 3 significant figures here. 43.3 then, right? And that is, atoms cancel, grams. Raise your hand. How many got 43.3 grams? That's almost everybody. Looks like pretty much everybody. That's good.